So, we are continuing with the air-jet texturing. Last time we had covered some definitions of the air-jet textured yarns, and we noted there are at least three major processes which are called the opening of the filaments, loop formation, entanglement. These are the three things which must happen before an air-jet textured yarn is useful and is produced, and some advantages in application of air-jet textured yarns. Today we will try to learn about some of the essential components of a typical air-jet texturing machine and their role, and how do we characterize an air-jet textured yarn. So, let us first look into some of the possible components in a full air-jet texturing machine. So, if you look at a line diagram of a machine, this looks a pretty complex thing with everything there. So, you have a creel from where you can pick up the yarn to be texturized. Interestingly, this can happen that you may have a fully drawn yarn for texturizing, or you can have a POY for texturizing. So, depending upon whether you have a fully drawn yarn or a POY, your threading sequence may be different. For example, if it is a fully drawn yarn, it may take a path like this and go here, and then from here go to air texturing zone. All right. So, you have a fully drawn yarn which can move in this way. Because it has already been drawn, so it does not need any drawing. In case you have a POY, which means this is not a fully drawn yarn, then this machine has a zone which is called a drawing zone. So, between these two sets of rollers, one can do the drawing. Now, so your threading sequence from the creel will be now different. So, you come this way and then go this way, and then you have a drawing zone. So, between these two rollers there will be drawing taking place. So, if you have a fully drawn yarn, you take a different path. If you have undrawn or a POY yarn, which is going to be the general raw material, in such a case then you take a different path and then go to a zone called a drawing zone. If I ask this at this time that what kind of a sequence this will be called, this should be a sequence where first there is drawing and then there is texturing. So, in some sense we are calling it a sequential draw texturing machine. Can we think that we will be able to do simultaneous draw texturing as well? Can we think or design a machine where instead of sequential draw texturing, which is the case which has been shown here, that if you have a POY, first you take it to drawing zone, then draw and then feed it to the texturing zone. So, what I just wanted to ask is, you think it is possible to design a machine where we can combine the drying and texturing in one process and make it sequential draw texturing machine the way we had done in a false twist system. Can we do it? No. Oh yes. Yes. All right. So, there is one response called the yes, that sequential or simultaneous draw texturing can be done. Any other response? No response. All right. So, the question is, can simultaneous draw texturing and which means we are talking about air jet texturing be done? So, somebody says yes, so you are making a design and other response has not come yet, that means it can be done. Other believe, or there is somebody who says it cannot be done. Yes? You saying something? So, I believe that there are three answers, a no and a yes and do not know. So, how many people believe that it can be done, which is yes? The one person who said that is also gone, no, it is there. So, we have at least one person saying that. How many people believe that it is no? So, after all the hard work, we have about 3 people who think it cannot be done, and the others obviously are in this range because the class is pretty big. All right. Okay. So, before we answer this question, you should obviously know approximately the basic steps that we had discussed last time for making an air jet textured yarn were opening, then loop formation, and third was entanglement. So, opening can take place, let us say whichever way it takes place, that the filaments get separated. How does the loop formation take place? Overfeed. So, this is an important thing. If overfeed has to take place, and then we ask this question. So, can you do drawing as well as overfeeding together? So, simultaneous draw texturing in air jet texturing machine cannot be done. So, I hope when next time somebody asks this question, everybody will have the same answer. That will be interesting. So, we come back to our own original sequence line diagram. So, it says that either you need a drawing, if you need, then you go to a drawing zone, first draw the machine, the yarn, and then feed it to the texturing zone. In the texturing zone, when it is fed, it is actually a fully drawn yarn when it is being fed to the texturing zone. So, between the texturing zone, what will be there? Some texturing must be occurring. That means you will give overfeeding, he said overfeeding. So, between this zone you will have some overfeed, Of course, you will have some air pressure, compressed air which will be there to do whatever little job. So, this is like a zone which is the texturing zone. So, theoretically in a air jet texturing machine, this is the zone which is because of which it is called air jet texturing machine. What we are doing before is the requirement of the material. So, no texturing is happening there. After that you see something called a mechanical stabilization zone. So, after texturing is complete, most of the machines would also have a mechanical stabilization zone. If you remember, we said air jet textured yarn will be successful yarn, useful yarn if entanglements are good. If the loops that have been formed can open, then it is not a good yarn. So, if you supply the yarn immediately after which has been just air jet texturized and give it to the user, he may complain that it has got very unacceptable instability, all right. If it is unacceptable instability, then obviously your material is going to come back. So, they say whatever, how will he find that it is unstable? Because maybe it is using as a warp yarn, there is tension. If there is tension, the loops will open. So, this is says why not we put the tension, so that let the loops be open in the manufacturing area, so that when you give it to the customer, this fellow is happy. So, there is something called a mechanical stabilization. What it means is you are giving tension, give tension in this zone. So, what will it actually mean is you are doing some amount of stretching, that is how you put the tension. So, you have overfeed and then you have a stretching. Then the machines may also have a thermal stabilization or a heat stabilization zone, which is just like you can see it is a tubular heater. It is a tubular heater where a yarn which has already been texturized, which has already been stabilized a bit, is now being passed through another heater. This will be used only if there is a thermoplastic yarn. If you have a viscose being air jet texturized, you do not have to use this zone, but what you will do is the heaters will not be switched on. The machine may still have, because you do not make a machine for viscose and the other machine for that. Okay. And then of course, after this it will go through oil application device. In case something has been lost, then you have already learnt the lesson in the false twist, this may be replenished. So, if you look at this whole machine, it looks like as big and as complex machine as any other machine. So, you have a creel from where the things will start. The creel will obviously have detecting systems, whether the yarn is broken, not broken, it is being fed, something will be there, and then you can take it through. Theoretically, you can also have another feeding system where all of them, let us say even if all of them are fully drawn, you may like to give different overfeed. So, within the same jet you may like to give different overfeed to different yarns, and what will that happen? It will be able to take some of the yarn to the surfaces of the surface of the yarn, some filaments will go into the core preferentially, because the overfeed may be less. So, you can have another system where different amount of overfeed can be given to different yarns, which are together being fixed, finally being fed to the air jet texturing zone. So, you can make fancy yarns, you can make core and effect yarns within the same thing, and of course, if one of them is a POY, other is a viscose. So, you can feed viscose directly, take the POY, let us say polyester, through the drawing zone, and finally, they go to the air jet texturing zone together, maybe at the same overfeed. If they go with the same overfeed, then they will get properly mixed. So, you will find polyester as well as viscose on the surface approximately probabilistically in equal amount. If you do a little bit of manipulation, that means polyester is given less overfeed, viscose is given more overfeed, then you will be able to get another yarn which will have large number of possibility of large amount of viscose on the surface and polyester mostly in core. So, that kind of thing will produce. And of course, all of them should be stabilized mechanically and then heat stabilized. So, the texturing zone, which is the heart of the machine, it looks like a black box. But it is the heart of the machine. If one opens the texturing zone, it may be a box. The box may have a lid which you can open, a lid which can be opened. It may have a threading sequence that the yarn is coming from somewhere and getting out. Between these two sets of rollers, you have overfeed. Of course, in between it may be connected to compressed air, and it may also have a device which is called a wetting device, where the yarn is initially given a little bit of moisture, applied a little bit of moisture before it enters the air jet. So, this so called texturing zone, which has got two sets of rollers where the overfeed can be done, you of course have an air jet which is the main component which is responsible for whatever is happening to the yarn, may have a supplementary component called a wetting device, and this whole thing is covered. Two things: once you cover, the noise level comes down, because this whole process will make some noise, you can do that. In case there is something called wetting happening, you may do, you may not do. Then there may be some spraying of moisture, so which may not go everywhere. So, it may remain contained within that small box, and you can drain it out in case there is a water which condense. So, you may have a drain. So, simple system, but still you may have a bit of a complex thing. So, what we do here? Obviously, in texturing zone you will probably try to have some control on the overfeed, you may like to have some control on the air pressure, you may like to have some control on wetting, and then becomes this is the main part of the machine. Drawing zone, obviously for the undrawn or POY machine materials only. If one uses, so it have two sets of goddets where there will be drawing taking place. So, you will give some amount of draw ratio here. based on the characteristic of the POY or undrawn yarn, so that finally you are able to get a fully drawn yarn at the end. It is written somewhere, there is a hot pin. What it means is that in case you have materials like polyester which needed to be drawn at a temperature higher than the room temperature, so you take it over those hot pins. So, temperature will rise and you will be able to do the drawing more effectively. In case you have materials like nylon where the glass temperature may be low and nylons can be drawn at room temperature also. So, you would not need a hot pin, or you may not hit the hot pin, all right, and you can do the drawing. So, once the drawing is done, so therefore, every machine will have a drawing zone, may be used, may not be used. The oiling device, it is only in case you have used a heater, and because the POY may be finished, spin finished with the same type of a spin finish as is being used for the POY for false twist. It may have components which can get evaporated, then you would require an oiling device. In case you are not using a thermoplastic yarn at all, then you do not need to use this. You can always bypass or just let it be there. So, that is the only reason why you may like to use an same type of oiling device, which is like a works on a kiss roll principle. So, we now understand why do we require a mechanical stabilization zone. Here you will do underfeeding. How much underfeed? This will depend on what have you done in your air jet texturing zone. Sometimes 4 to 5% stretch you may give, so that loops which are not entangled very much, they get opened, and entanglements which were probably less tight may become tighter. So, in the next time when you want to use this, you will find the entanglements are better, because there may be opening and some things which are, let us say, covering the rest of the bundle, they may, when you open, they may become tighter, and once they become tighter, obviously entanglement is more effective, and so at a later stage this may not open. So, you will be producing yarn with less instability. This is to satisfy your customer. Then we said thermal stabilization, in case it is required, obviously it is for only if you are using thermoplastic yarns. In this zone, a thermoplastic yarn, whenever it is going to be heated, it will shrink. A fully drawn yarn, when heated, a thermoplastic fully drawn yarn, when heated, will shrink. It should. So, what would happen? The yarn that you are giving is a fully drawn yarn, but already air jet texturized. This is not a parallel bundle of filament. So, the yarn may have loops protruding and entangled maybe. So, what would happen? When they shrink, there is a possibility that this may shrink like this. There is a possibility that it may shrink like this. there is a possibility that the loop size which is here, the loop shrinks by itself, which is entangled somewhere there. So, a large loop after thermal treatment may become a smaller loop. But if there is something called an entanglement like this will also shrink and it will again become tighter. So, whatever you were trying to do with the mechanical stabilization, this will only be accentuated further. The larger loops can become small, the yarn overall can shrink, the entanglements can become tighter, and so instability will reduce. So, instability reduces. So, this is a good thing to happen from the customer point of view and therefore, for the person who is a manufacturer also. So, what will you do here? Underfeed or overfeed in this zone? So, we will give some overfeed. Does it mean there will be no tension in the yarn? Because you are overfeeding, no tension in the yarn? Yes or no? There will be tension because it is shrink, it will shrink. So, you will not have additional length. So, that additional length which we are giving as an overfeed will become less because it shrinks. So, you will give overfeed here. Okay. So, now you have, look at this drawing zone, you are obviously giving a draw ratio stretching. Air jet texturing zone, you are overfeeding. Mechanical stabilization, you are stretching. In thermal zone, you are overfeeding. So, you are not making life easy for anyone. So, theoretically everywhere there is a parameter which can be controlled. You go to drawing parameters have to be controlled. If you go to heat stabilization, that parameter has to be controlled. If you mechanical stabilization, that parameter has to be optimized. Air jet of course has to be done. So, we are looking at only air jet, but if you look at the whole machine, you got many more components, all of them will have to be handled correctly. If you make mistakes in one, so you will have some consequences also. So, before we say that optimization parameters etc., so we should know exactly how would you like to characterize an air jet textured yarn. In false twist, if you remember, we had crimp rigidity, crimp stability etc., which were the important characterization technique methods. Here we have to do it in different way. Why? Because this yarn has no stretch, remember. There is only, we expect only bulk to increase. So, obviously, we say bulk must be measured. So, bulk is one part which you may be interested. So, people may like to have many types of methods, you can still add on to these one way or the other. Instability is one important parameter which must be measured, because if instability is more, there is no point in, you can't sell the yarn. And that is the reason, if you remember, our machine speeds originally have been very slow, so that you could at least do something to the instability. Physical bulk percentage. So, you want to know, you started from whatever bulk, that the specific volume, and at the end of the texturizing process, complete texturizing process, which may have gone through the air jet texturing, may have gone to mechanical stabilization, may have gone to a thermal stabilization. After the end of the day, what is the final increase in the bulk, that you will be interested. Shrinkage, anybody will like to measure any time whenever you want to do the shrinkage. Hot water shrinkage means that you are actually looking at thermoplastic material which actually can get affected by thermal treatment. This is one, but you can measure any kind of shrinkage. One always believes that at room temperature shrinkage may be less. So, you go for a little higher and look at it, because with say washing machine or anything else the temperatures could be different. Surface characteristics means that you obviously this yarn does not look like the way it used to be. It has got loops, crinkles, and we said that it looks more like a spun yarn. Whether it does or not, one may be interested in measuring some of the characteristics which may be connected to what the above three properties are there in some way. Of course, you may like to worry about tenacity. If it is, let us say, a non-thermoplastic yarn is gone through mechanical process which is the edge texturing. So, no microstructural morphological changes are going to take place within the filament. We expect that. If you do thermal stabilization, of course, you can expect something, but if you are not doing any thermal stabilization, then you do not expect any intra fiber morphological change, no crystallinity change, no orientation change, no moduli change should take place within the filaments. What about the tenacity? In the other case, which is the false twist texturing, we said the tenacity of the textured yarn was lower, right, because lot of morphological change were taking place, orientation had changed, crystallization was taking place, and so on and so forth. Here, what do you think? I mean, we must be interested in measuring tenacity because you have to sell a yarn. So, I am just giving this question assuming that there is no thermoplastic yarn, or even if there is thermoplastic yarn, we have not gone through the thermal stabilization zone. What should be happening to the tenacity compared to the parent yarn that you have taken? And here you can appreciate the parent yarn finally, which is going into the texturing zone, is a fully drawn yarn. Yeah. Yes, not much change. Let me go back here. Now, what are we looking at? Tenacity of a textured yarn. Air jet textured yarn. So, one response I received just now is something called not much of a change. Any other response? Instead of, let us say, response, we put it in terms of tenacity, no change. We are comparing with parent yarn, it will increase, it will decrease. Let us put it all the options in life that we have. Law of trichotomy. So, how many people believe there is no change? How many people believe? You can raise your hands. At least one should have been there. Okay, that is also gone. How many people believe it will increase? So, there are at least 2 or 3 people who believe that it can increase. And how many people believe there will be decreasing? Well, there will be more number of people who believe that there will be decrease. And rest, of course, another thing, do not know. Okay. But in any case, why do people who think it should increase, they believe that it should increase. Those who said that they can increase, why should it increase? Because of entanglements. That means there are entanglements, okay. So, because of entanglements, which are not there in the other yarn, it may increase because there is a compressive force, right. The people who believe that is going to decrease, why do they believe that it will decrease? So, it was not just a polling, it has its consequences. You elect your own government, then you will have to basically see what happens. Okay. So, why do you believe that there is no change? Oh no, there is a decrease, or was it an arbitrary nice thought? Yes?
Filament orientation is decreased.
All right. So, one answer has come that the filaments after air jet texturing are not parallel to each other. In a fully drawn yarn before texturing, all the filaments were parallel to each other. And now, after all this loop formation, entanglements, the filaments are not parallel to each other, and therefore, they are not contributing to the tenacity or the strength. Some of them may be almost oblique to the direction of the force which is being applied. So, the percentage of the filaments contributing towards the yarn tenacity, textured yarn tenacity may be less, and so it decreases. So, this is not right, this is not right, change of course must take place, we do not know what is this. The tenacity of the air jet textured yarns will decrease after texturing because the filaments are not parallel to each other, the contribution is low. Not so much so, if you really produce a very good air jet textured yarn, the tenacity can go down by 40%, 50%, which was not even the case when the false twist texturing was done. You understand? A process which does not change anything in the yarn can finally change the tenacity, reduce the tenacity significantly. So, somebody should be interested in measuring tenacity. If it does change, then it does change. So, in fact, if we just put it the other way, if you do a bad job in air jet texturing, that means instability is high, your tenacity may be high, not higher than the parent yarn. But if you have done a good texturing, where your entanglements are very good, loops have been formed quite a lot, bulk has increased tremendously, you say that tenacity has gone down and significant. Of course, you will be interested to know about the modulus, which will also mean that how much resistance is being offered, and extension break. These are some of the things which you may be able to measure in this same normal way, the way you measure anything. This yarn obviously does not have stretch, instability. So, what do? You put a weight which is W1, you can call it, to measure the length of the yarn. Let us say whatever the length of the yarn is, and then you put another load which is heavier. The W1 is about 0.01 grams per denier, W2 is 0.33. DuPont somehow decided that this is the kind of load that we will have. So, this is one of the processes, there are other processes also. So, then you remove the load, the heavy load, and under the small load it is retracting. So, it retracts. So, initially you have some load just to measure the length, then you put a heavy load, then it extends, and then maybe it recovers, but does not go back to the same level. But under the load which is the same load, which is W1, W1. And then see what is the permanent change in length. So, you might find the length is permanently increased. So, obviously, you do not want permanent increase in length to be high. If the length increase is more than 10%, I am sure people are not going to be happy. I mean, everybody is happy having a more number of meters of the yarn. Instead of 1 kilometer, you have 1.25 kilometers of the yarn. So, you can be happy, but the mass is same, and of course, it has opened, and so you do not know exactly what you are going to do. How do you control your processes? So, that is one method of measuring instability. You will want the instability to be as less as possible. So, when you say I am going to optimize in terms of pressure, in terms of overfeed, in terms of anything else, you will be tempted to first measure instability. It is the reverse of the stability, but that is how people believe they like to measure rather than measure stability. You could have done the reverse and say stability of the yarn, but they somehow got stuck to the instability, which had caused more problems, and so this is how you work around. Is that okay? The bulk. Bulk means specific volume. So, how would you measure the physical bulk? Now, you have a yarn which has been produced, and now you have the, you see the bulk is increased. Now, I want to measure. How do we measure? Suppose we want to measure that there was a parent yarn, we have something, and now you want to measure the textured yarn. What are the possible ways in which you can measure? Let us put it this way. Can you say something? What about denier? Can it be used? Cannot be used. What can be used then? How would you like to measure? Will the denier change or not? Of the, will it increase or decrease? Yeah? It should increase, I believe. Why? Because you have given some overfeed. For the same length of this new yarn, you have more mass. Is it true or not? Okay. So, overfeed, the denier are in some ways related, but after giving overfeed you may have given mechanical stabilization. So, overfeed may be related, but you are undoing something, one does not know. There may be some thermal shrinkage in case you are looking at, then it will do something else. But finally, we have to have some way of measurement. So, what I do is tell you exactly what people do, and then you can think of many other methods also. So, they would measure parent yarn package density. You make a package. So, they measure, let us say, package density, and then you have a textured yarn which also is wound on a package, and you measure the package density. And so, the bulk is defined as this simple term, but that is not the only way you can measure the bulk. There is a reason why people like to measure the bulk like this. If suppose you have a yarn which has got various types of loops, and you want to measure the bulk. Linear change is no difficulty, right? You can measure the length and have the mass, and so everything is fine. But that is not necessarily gets correlated with the bulk. The contribution of this versus this to the bulk may be different. If suppose you compress, which loop is likely to give you more bulk, a smaller loop or a larger loop? Larger loop will give you higher bulk, right? But it does not happen, because the larger loop's rigidity is so less, you compress, it just falls flat. So, when you touch and say, oh yeah, there is bulky, you say this fellow is not contributing. The smaller loop, if it is done, if you try to compress, this fellow actually resists compression, does not want to change, and if you have large number of small loops versus small number of large loops in the same overfeed, by changing, let us say, the condition of compressed air, right, the pressure, and you might create more number of larger loops or smaller number of larger loops. So, based on that, the effective bulk will be different, and therefore, people said that why not wind it on a package and then see which one is contributing more, which one is contribution less. Instead of that, let us say wind it under a specified tension, and you should be then able to see actual value of a bulk increase in practical sense, although other methods cannot be denied that they cannot be used. All right. So, we will stop here and then pick it up next time.